Welcome to a course on complex analysis. In this lecture, we are going to talk about different types of curves that are available in complex plane. Let us explore. I said that we are going to talk about the different types of curves in the complex plane. So the first thing that we are going to talk is contours. Okay. So, but before introducing what do we mean by a contour, we start with some basic things. That is a set of points z, which is an order pair xy in the complex plane. This one is said to be an arc if your x takes the form x of t and y takes the form y of t for t lying between a and b. So we mark this as equation 1, where your coordinates x and y, okay, now they are functions of t. They are continuous functions of the real parameter t. Okay, now from this definition you may very well notice that a complex value is said to be an arc if the coordinates are functions of some real parameter t. Okay, so from this definition, actually this is a definition. So this definition establishes a continuous mapping of the interval AB into xy or z plane. We may either call this as xy plane or z plane, and the image points are ordered according to increasing value of t. So what we shall do is that we shall write z as z of t with t lying between a and b, and we mark this as equation 2, where your z of t is x of t plus iota times of y of t. Okay, so we have these things. Now we are going to talk about the next definition, that is the arc. Okay, so whenever I say the term arc, you must be knowing that it is the set of points in the complex plane satisfying those conditions. That is, the coordinate functions has to be a functions of some other variable t. Okay, the arc is a simple arc or a Jordan arc if it does not cross itself. Okay, I think if I give you some pictorial representations, you can easily view these things. This is my xy plane. Okay, and arc means I'll have to collect the collection of points. Okay, I'll have to choose some what an interval. Based on that interval, I must be able to identify some x of t and y of t. With those things, I'll have to collect some points in the xy plane, and those set of points I call it as curve, sorry, an arc. So this is an example of arc. Similarly, I can give you one more example, like consider this as a plane. If you consider some circle, this is also an arc. Okay, and if you consider some straight line, it is also an arc. Okay, this goes like this, and this goes like this and moves this way and move this way and move this way. This is also an arc. Okay, and this is also an arc. This is also an arc. These are some examples of arcs. I have given you several examples of arc. I am not giving the parametric representation of these things, but to make the idea clear to you people, I have drawn several diagrams. All these are called as an arc. Okay, so here what they are saying in the definition of a simple arc, if it does not cross itself, which means there must be no intersecting point of the curve with itself. Okay, for example, if you consider let me put the tick marks in green color so that you can understand. Okay, here if you see, you have an cut here, which means they are intersecting. The curve intersects itself. So this cannot be a simple arc or Jordan arc. Okay, Jordan arc is another name for the simple arc. Here there is no cut by itself, so it is a simple arc. Similarly, here also there is no cutting; they are joined. Okay, since there are no cutting, this is also a simple arc. This is not a simple arc since it intersects at two different points. This is an example of simple arc. This is also an example of simple arc. Okay, so if it does not cross itself, mathematically, how do we represent this one? That is, an arc is said to be simple if z of t1 is not equal z of t2 whenever your t1 is different from t2. If you recall from your analysis, okay, basic analysis, you can see this is the definition of a 1-1 mapping. If your mapping is 1-1, then the arc is said to be simple arc. Okay, so the next one is when the arc C is simple except for the fact that z of b, okay, I think you may not be able to see what I write there. Z of b equals z of a, such arc is called simple closed curve or a Jordan curve. I have with those diagrams, I have provided you some examples where you can notice very well that only in this diagram we have a common point. Okay, which means at some point, okay, from here to here, n points meet together. So only at that point the condition of being 1-1 fails to hold. If that is the only point in which the condition fails to hold, then we say such kind of an arc as simple closed curve or simply a Jordan curve. So among these things, this is the only example which is a Jordan curve, right? So or a Jordan curve. Okay, I think I'll have to write one more point regarding Jordan curve. So such a curve is positively oriented when it is in when it is in the counter clockwise direction. In our usual sense, we call this as a counterclockwise direction, but in mathematical language, in this terms of science language, this direction, okay, so this direction is called as the positive orientation or positive direction. Now let us get into some examples. So let me explain these things with an examples. The first example that we are going to see is z is given to be x plus iota times of x when 0 less than x less than 1, and is x plus iota when 1 less than or equals x less than or equals 2. Okay, now we'll have to draw this curve and identify whether this is a simple arc or simply an arc. Okay, all those things we'll do now. Okay, from 0 to 1, what is happening? Let me consider this as 0, and let me consider this as 1, and let me consider this as 2. Okay, x is varying, so I don't have to bother about y, right? So when x is 1, I have x plus iota times of x. So in a coordinate system, this is simply x comma x. When you collect the points, when you try to collect the collection of points such that x varies from 0 to 1, you can very well notice that it is a straight line of this sort from 0 to 1. Okay, so if this is 1 and if this is 1 in this direction, so this is going to be the point, and this is your curve x plus iota times of x. Once we have done this, next in this interval 1 to 2, what is going to be the case? It is x comma I, which means it is going let me draw that in a different color. So it is going to be the collection of points x comma 1 where x lie between 1 and 2. So if you try to, which means what? In the graph from 1 to 2, your second coordinate, that is your y value being 1, is fixed. Your x is going to be varied, which means you will have this one. Okay, if you don't have any idea of how to draw these things, let me put these things in a different setup. Okay, here what is fixed is that x is varying, which means your y of x is 1, where your x in this interval. I think now you people can plot these things, right? Similarly, for the first case, here your y of x is x, where x takes the values in this interval. Okay, if you put these things in this form, you can easily draw these things, and you notice that this is happening. Okay, here the curve does not cut itself. Here the curve does not cut itself. Hence, this is a simple arc. Right? Now let us move to the next example. We are given z equals e to the power iota times of theta, 0 less than or equals theta less than or equals 2 pi. Right? So when we try to plot these things, right? Sorry. Yeah. So usually a complex value is written in the form of z equals r e to the power iota times of theta, where theta is what? Tan inverse of y upon x, or this is the argument of c, or we may write it as simply argument or principal argument, whatsoever we like. And this r is the absolute value of z. Okay, so this is the, if you are about to take if you are about to take some point in the space and connect this with the origin, so the distance, these points, this distance is the value of r, right? So here, from the thing, from the given information, if you observe, so from the given information, your r value is 1. So we choose some point, okay? You can choose it anywhere, okay? Whether you choose this side or this side, or you can choose it anywhere, okay? You will have to choose some point, okay? For simplicity purpose, let me choose this point 1 on the x-axis itself, okay? So this is my distance 1. Now if okay, now let me explain, okay, let us recall the things. If this is my point P, this distance is r and this angle is theta, okay? Here your r value is fixed but your theta value is varying. So when your theta value is 0, exactly it lies on the x-axis. When your theta increases positively, okay, so when your theta increases positively, it moves like this, okay? So actually it moves like this and you will get a circle. So I am not good at drawing, as you people know, I have said this in many lectures. You will have a circle of radius 1, okay, because your theta is varying from 0 to 2 pi. Suppose if it is given 0 to pi, your circle is a semicircle only on the positive y, okay? Only in the upper half you will have these things, right? So we have drawn these things. This is an example of what? Jordan curve, okay? Only at those end points the function meet, right? Generally equation of a circle is your z z naught plus r e to the power iota times of theta, where theta vary from 0 to 2 pi. This tells you that your z naught is the center and r is the radius, okay? Now we'll move to the next example. Z equals e to the power minus iota theta, where theta lie between 0 and 2 pi, okay? So the same thing here also. Here your r value is 1. So let me choose a point here, and when my theta increases, here I'll have to move it in the negative direction. So it moves like this, and you would get you will get a circle, but it is moving in this direction, whereas in the previous case it is moving in, sorry, it is moving in this direction, okay? Here it is in the positive direction, here it is in the negative direction, okay? it moves this way. Next we have an example, that is z equals e to the power iota times of 2 theta, where your theta varies from 0 to 2 pi, okay? Even here when you try to plot, here also your r value is 1. So this is going to be, and when your theta increases, it moves like this, and when your theta value is pi, actually when your theta value is pi by 2, it comes here, right? Since it is 2 times of theta. And So when your theta value is pi, it completes a circle, and it again goes on the same path for the second time when your so one circle is completed when your theta lies between 0 to pi, and the second circle will be completed when your theta ranges from pi to 2 pi. Okay, since it is given like this. Okay, so these are some examples here, but you'll have to pay attention and understand one more thing, that is, we have seen z equals c to the power iota times of theta, z equals e to the power minus iota times of theta, z equals e to the power iota times of 2 theta. The curves are same. When we plainly look at the curves are exactly the same, but these three are different because the first one is positively oriented, the second one is negatively oriented, and the third one is transversed twice in the positive direction, right? So even though the diagram looks the same, they are different. That is what you will have to clearly understand in this lecture, right? In the upcoming lectures, we are going to continue our discussions on contours. Till now, we have not introduced what do we mean by contour. So that is what we are going to do in the next lecture. Thank you.